So let me start with a disclaimer that I'm going to talk about El Nino, which is certainly a climate issue, but I am far from a climate scientist. I got dragged into working on this problem by a postdoc several years ago and became fascinated by it and have done a lot of reading and playing around with data myself, but I haven't really connected all that well with the community of people who study El Nino. I guess Hank Dijkstra is much more in this world than I am. So I'm going to start by with a few slides talking about what El Nino are. And the closest thing I would think to some sort of official definition of El Nino is from a website of NOAA, the federal agency in this country that deals with oceans and atmospheres and so forth. Now let's read this. It says, El Nino and La Nina are opposite phases of the El Nino Southern Oscillation, which is abbreviated Enso Cycle. The Enso Cycle is a scientific term that describes the fluctuations in temperature between the ocean and atmosphere in the east central equatorial Pacific. And then it gives the location a bit more precisely. La Nina is sometimes referred to as the cold phase of Enso, and El Nino as the warm phase of Enso. These deviations from normal surface temperatures can have large-scale impacts not only on ocean processes, but also in global weather and climate. El Nino and La Nina episodes typically last 9 to 12 months, but some prolonged events may last for years. While their frequency can be quite irregular, El Nino and La Nina events occur on average every 2 to 7 years. Typically, El Nino occurs more frequently than La Nina. The first detailed observations of an strong El Nino event occurred during 1957-58, when there was something that was called the International Geophysical Year, IGY. And it just happened to coincide with this. And people were so blown away by what they observed that they created a array of buoys that are still out in the equatorial Pacific in order to monitor these sorts of events. But here are a few slides that illustrate this further. So this is a picture of mean ocean surface temperature globally. And as you would expect, what you see is that the temperature is roughly correlated with latitude. But there are some places where that seems to break down in some ways. And the most apparent, most striking breakdown is in the equatorial Pacific, where there's this tongue sticking out from the coast of South America, where the sea surface temperatures are much colder than they are along the rest of the equator in the oceans. In addition to the average temperatures, we're interested in anomalies and the departures from the means. And again, if you look at a global map of these, there are places where that are striking in that you have much larger variation of the temperatures than in other places. again, the largest of these regions is in this tongue in the equatorial Pacific. So that's the location where El Nino and La Nina occur. It's also notable that the other places where you see these large deviations tend to be along coastal regions, one of which is in the North Atlantic of here. This is an effect of the Gulf Stream and the variations in the Gulf Stream. So the last time that there was a large El Nino event was 3 years ago now, in the winter of 2015-2016. And this is pulling off of one of the federal sites, a daily map of sea surface temperatures. And it's showing the anomalies compared to the averages. And you can see now that there's this long region in the equatorial Pacific in which the anomaly is positive. The temperatures are warmer than they normally are in this region. So this is the region where things were usually cold, but they're warmer now than they typically are. And that's in the middle of El Nino. Right? This is the height of El Nino, and the anomalies are in the order of about 4 to 5 degrees centigrade from their averages. So that's a considerable warming that occurs. One of the other aspects of El Nino is that it really is a coupled atmospheric ocean phenomenon. And this is a graph that's taken from one of Henk Dijkstra's book that shows the correlation between the average sea surface temperature in a region that's referred to as Nino 3 in the equatorial Pacific, and the pressure difference in the atmosphere between Tahiti and Darwin. So this is often abbreviated SOI, Southern Oscillation Index. And you can see in this that the sea surface temperatures are in blue in this diagram. Red are the SOI data, and they appear to be anti-correlated. Right? When there is colder sea surface temperatures, this tends to be associated with large positive values of this SOI index and vice versa. So this is evidence that suggests that the El Nino phenomenon is something that really involves both the ocean and the atmosphere. So again, from Henk's book, here's a diagram that represents some of the physical processes that are involved in the equatorial Pacific. So in the atmosphere, there's a so-called Walker circulation, which you can think of it being in a vertical plane, that there tend to be winds that flow from east to west, rise over the western Pacific, and then go back from west to east at higher altitude, and then subside again when you get close to the coast. That's sort of different from the Coriolis forces that are associated with the Earth's rotation, tend to generate winds that go from west to east. So this is going in the opposite direction. And the reason that this happens is that the air that is flowing sort of converges at the equator, and that convergence causes a band in which the winds blow in the opposite directions. So the wind stress on the surface of the ocean tends to take water with it, to push water with it. And in this case, it's pushing water away from the coast of South America to the west. And as it does that, it creates an upwelling of water that come from depths, get closer to the surface, and make the sea surface temperatures much colder than they otherwise would be, and create this cold tongue that you saw in the earlier transparencies. So there are a variety of dynamic processes that are involved in creating El Nino and lead to breakdown in this sort of static pattern that I described. Within the ocean, there tend to be two kinds of large-scale waves that occur. One kind are called Kelvin waves that you can think of as being sort of a wave that propagates often from west to east. Think of it as being like the waves that you see when you go down to the beach and look at the ocean. There also are Rossby waves that tend to be more vortex-like motion, more like the sort of things that you see with large-scale weather patterns in the atmosphere. And those also have an effect on the dynamics of what's happening in the equatorial Pacific. So this is a transparency which is probably too small for you to really see the details. From a recent paper by Timmerman and others in Nature that presents a kind of overview of what we know about El Nino and so forth. And this presents a sort of caricature of the events that occur during the Enso cycle. So below the ocean surface, there is a steep temperature gradient at a certain depth that is called the thermocline. And because of the currents that I described, the thermocline tends to be considerably deeper in the western Pacific than it is in the eastern Pacific. And when an El Nino occurs, there typically are there's sort of phenomenon called western wind bursts that occur in the western Pacific, and it generates one of these Kelvin waves that will push the warmer water that is above the thermocline towards the east, push the thermocline down, and the sea surface temperatures in the eastern Pacific will become much warmer. And that's when those temperatures sort of equilibrate or come close to equilibrating across the whole Pacific, that's the El Nino event that occurs. There's a recovery from the El Nino event after it occurs that tends to be associated with the phenomena that take place in the north-south direction, transverse to this direction that allow a kind of recovery of the colder sea surface temperatures in the eastern Pacific. So, as I said, the phenomenon was really first observed and understood largely. I mean, people knew about El Niños from what they saw off the coast of South America for centuries. But the beginning of an appreciation that this was a whole ocean phenomena tended to be associated with the International Geophysical Year. And this sort of, the top band up here is a reconstruction of the observational record plotting the average sea surface temperatures in this Niño 3 region of the Central Pacific. And clearly it's something, this is something that we want to understand much better, and efforts have been made to build models. And the second half of the talk, I'm going to talk about low-dimensional dynamical system model that I've worked with. But there also have been attempts to reproduce these phenomena in simulations of global climate models. So one of the models that has been studied most extensively in this regard, especially by Andrew Wittenberg and collaborators, is the Geophysical Fluid Dynamics Lab model CM 2.1 in Princeton. During maybe 15 years or so ago now, they ran this model for a whole year on a cluster of workstations. It was a big computer at the time, and did a 2,000-year simulation in order to study, well, this is a simulation of the whole globe, but one of the things that they were particularly interested in doing was to see whether this would reproduce the sort of phenomena that one sees in El Nino. And it did. The colored regions in this diagram are showing different epochs in which the characteristics of how frequently the El Niños occur and what their magnitudes are have somewhat different characteristics. And it's been sort of the observational record that the time scale that we're interested in this is more or less a decadal time scale. And so the amount of actual data that we have, observational data, is really small. We can use these large-scale simulations as a sort of surrogate in trying to understand the dynamical characteristics of the process. So as someone who comes from dynamical systems theory, one of the things that I've worked with and am interested in here is dimension reduction, trying to see to what extent the phenomena that occur appear to be something that can be represented in low-dimensional models. And there are a variety of patterns and techniques that have been developed in order to do this. And I'm going to spend a few minutes showing you some of my efforts to look at the data from this Princeton simulation that are available on the web and see what they do. Let me spend just a couple of minutes talking about some of the ideas. So the image that one has is that you have a phase space for the system, which is very high dimensional, millions. But you think of trajectories as settling onto some sort of low-dimensional invariant set, and there being attractors for the system sitting inside these invariant sets. And you'd like to understand whether you can sort of reduce the dynamics to something that is representative of these low-dimensional things. Closely related to the low dimensionality is the idea of recurrence. Do you see states recur that you've seen before? If I have a ball in a space of dimension d, and or a cube, and I chop it up into the subcubes that are 1/10 the diameter in each direction, then the number of smaller cubes I get is 10 to the d. So if I just randomly pick points and ask how long does it take for me to get 2 points in the same cube, that time is going to grow exponentially with the dimension d. It's going to be comparable to the 10 to the d. If I have something that's 100-dimensional, and I ask, do I expect to see any sort of recurrence? The answer is not in the lifetime of the universe. On the other hand, when you look at the data from the Central Pacific, you do see pretty good recurrences. And one of the other aspects that's associated to chaotic systems is the idea of sensitive dependence to initial conditions. The trajectories will sort of spread out from each other, and they'll do that at exponential rates. So there are a set of techniques, and I'm not going to talk about these in any detail at all, that have been developed as tools for trying to analyze these characteristics of things that we want to apply to the data from the large climate simulation. And we're going to do that sort of with a hypothesis sitting in the background that the region of the Central Pacific where El Nino occurs is something that is isolated from the rest of the ocean. There's a relatively small effect of the dynamics elsewhere on here, so that we can sort of ask, if we just focus upon this region, is this behaving like a low-dimensional dynamic system? So one of the things that you can do are to compute things that are called empirical orthogonal functions or principal modes. You do some version of principal components analysis in order to identify what appear to be the most important modes in the system. And in this diagram, the top row is the observational data. And the bottom 3 rows are 3 of these different epochs selected out of the simulation. And apart from the fact that these two sort of look like they should be reversed, you get very consistent results as to what the main principal modes in the system are. This is a computation that I did to look at recurrences in the system, in which I simply take the region, measure how far apart are the states of the system from each other over the times in the system, and in order to not confound this with seasonal effects, I did this with time steps of a year, even though the data is archived with time steps of a month. And you find that there are some states that are much closer to most of the rest of the states. There's some states that are rather outliers, but they're pretty good recurrences.
Explain.
Sorry?
Explain this in more detail. What are we
So here I'm taking, I have 500 years of data, that's what's on the web. I take pairs of observations from a certain rectangle in the Central Pacific. I measured the distance between the sea surface temperatures in those two different rectangles. And then that's what's plotted here. So
it's hard to see the label. Maybe we just
it's hard to see the labels. This is the first time in years, and the vertical scale is the second time in years. So this is a 500 by 500 discrete plot. Doesn't quite look like that. And so one of the things that you can do in order to get a better sense of some of this stuff, these recurrences, I can take a pair of states that are close to one of the, that are at one of the closest recurrences that I see, and draw for the sea surface temperature. And I've done this in, I believe, 3-month increments. And you can see that the thing in the third column here is the difference between these two. So you start off with things that are very similar to one another. After about roughly 3 years or so, these states have drifted apart from each other, and you get fairly big differences. But they come close together, they go apart again. One of the ways of trying to estimate dimension, there's an algorithm that one version that was then most widely used due to Rossberger and Procaccia. But you can calculate fractal dimensions based upon the idea that if I have a ball in a space of dimension d of radius r, then its volume grows like r to the d. Right? So volume grows like the dimension power of the radius. If one assumes that the data one is looking at is sampled from an appropriate invariant measure, again, there's a lot of theory behind this, one can do a plot of the logarithm of the radius and the logarithm of the volume as measured by the proportion of observations that you have that are within that radius of the base point that you pick. And so what this diagram shows is that I take all of my 500 points in the data set. I guess I'm doing this with the monthly data, 6,000. I take each of those points and I compute this graph of volume versus radius on a log scale. I look for a region where things are roughly linear, and the region that I picked between the two horizontal lines there, and then try to calculate the dimensions by doing fits to that. And so here's a histogram of what the slopes are. And it's highly peaked. The peak is somewhere around 5. Okay, and that agrees with estimates that have been done using other methods of what sort of dimension you expect to see in the system. So this is evidence that there is low dimensional behavior in this, in Enso, in the phenomenon that we're looking at. On the other hand, this is something that I find very puzzling. One of the experiments that Wittenberg his collaborators did was to take some states, make very small perturbations to those states, and then run forward simulations from those states. And if it was a low-dimensional dynamical system, you would expect sort of a coherent way in which the things would spread in order to eventually give rise to sensitive dependence to initial conditions. But what they find is that things seem to spread much more rapidly than one would expect. So on very short time scales, the system is behaving much more, I hesitate to use the word random, but it's not behaving in the way that I would expect from a low-dimensional dynamical system.
So what do you mean exactly? There is no exponential separation?
There's no apparent exponential separation that you see here in that you're doing, this is like an ensemble prediction in weather forecasting, and these things are just going all over the place. That the black things here are the reference trajectories, and the blues are showing the temperatures. There's no structure that is visible here. I'd really like to reproduce this experiment, but I don't have access to the model, so that's another issue. Okay, so now I'm going to switch gears. I don't have a lot of time left. And talk about a three-dimensional vector field that is a reduced model for this whole phenomenon. This model was originally developed by Fei-Fei Jin. It has three variables that you can think of as being, in this representation, it's the temperature difference between the eastern and western Pacific, the temperature in the western Pacific, and the depth of the thermocline in the western Pacific. And there are two nonlinear terms in the model which in a hand-waving fashion are associated with the east-west advection of temperature anomalies by the wind. Those are the effects of the you can think of this as being similar to the Kelvin waves. And then there's an additional nonlinear term that's represented by the hyperbolic tangent that is intuitively thought of as being associated with north-south transport of fluid in the eastern Pacific. One can readily do simulations of this model, and among the states that one sees are ones that are reminiscent of the Enso cycle, in which you see large variations in the temperature in the eastern Pacific. I studied this model with Andrew Roberts, who's a postdoc here, who got me involved in this. And I joined a project in which they said, well, we want to think of this as being a two-time scale system, as a system which has slow dynamics and fast dynamics, and bring the techniques from that theory to bear upon this. And I'm going to not say anything about that theory, but simply show some of the results here, is that if you do that and you go to a singular limit in which you think of the system evolving on a slow time scale, then you get cycles that look very much like the cycles that you saw a couple of transparencies before. So this, thinking of this as a slow fast system is something that seems to be pretty reasonable. There are a lot of techniques that one can now bring to bear and do bifurcation analysis on this model, study different characteristics that it has. And one of the questions that we asked when we did this is, if you look at the predictability of the Enso cycle, what does that look like in the context of this very low-dimensional model? So, can you see the kind of irregularity in the low-dimensional model that you tend to see in the observations and the large-scale simulations as well? So, one of the things we found were parameter values in this three-dimensional model in which there are two different attractors, one of which has significantly smaller amplitude than the other one, drawn in red here. And in this case, it's chaotic. That's not particularly here or there. And then the green trajectory is like the trajectory that you saw before, that has these strong El Nino events. And they occur with a time scale that's on the order of 5 to 10 years. One of the things that we can do, and we look at this and we can say, well, what do the basins of attraction for the two attractors look like? Right? Which initial conditions are going to go to the red attractor and which are going to go to the green attractor? So here is a region in a cross-section with the flow. And the trajectories that start there go to the red attractor. The intersection of the red attractor with the cross-section is drawn in red here. The blue points here go to the green attractor, and that's a periodic orbit that comes through here just a couple of times, and you see the intersections with those. Now, this three-dimensional model doesn't have any seasonality in it. Right? There's no annual variation of things. There's no stochasticity. If we put a little bit of either of those in, we have a little bit of periodic forcing, or we put a small random forcing into the system, then you get behavior that looks like this. So Gary Froyland has taught us about almost invariant sets. You can think of these attractors as becoming almost invariant sets, and there will be fairly long periods of time in which the attractor is in the vicinity of one or the other, and then transitions in which it goes to the other. If you go back and you look at the simulations of the large climate model, this is just showing that, again, that there are epochs in which the variability, the sort of range of variation of the sea surface temperature is much smaller during some periods than it is during others. You get, this low-dimensional model in some ways is mimicking some of this. So this prompts us to ask the question of, well, how predictable is this phenomenon? 3 years ago, we had a very strong El Nino event. If we just take the frequency of the events that we've observed then we would predict that sometime in the next 5 to maybe 15 years, we're going to see the next strong event. But there have also been periods, it would seem, in which the strong events disappear and go away, and we can go for decades without having them. If we look at the three-dimensional model, we can ask, well, you know, in that setting, can we predict how frequently things are going to occur? So this transparency shows the effect of high sensitivity in the GEN model. Here, an array of initial conditions has been selected along a segment here that's a length that's about 10 to the -4. It goes through a few cycles, and then that gets amplified into something that's order 1. So there's some places where things are really big. We can compute things that are called finite time Lyapunov exponents. It's another measure of the spreading of trajectories. And we find that there are sort of strips in the phase space where we get very large finite time Lyapunov exponents that seem to be associated with the spreading of the trajectories. We can go back and look at the time series that I showed you where we computed transitions from where it goes from one state to the other in the force model, and try to see whether there's any apparent pattern in the lengths of those epochs. How long does it stay close to one state? How long before it goes to the next state? If we do a scatter plot of two successive things, it just all over the place. And if we calculate a histogram of the durations on a log scale, it appears to be rather like a Poisson process. So there doesn't seem to really be very much that, I think this is the last transparency. There doesn't really seem to be very much, even in the three-dimensional model, when we look at one of these states, that we can say that, well, this is what happened in this decadal cycle, and that's going to help me to predict what's going to happen in the next decadal cycle. That appears to be something which, at least at the level of this sort of analysis, appears to behave randomly. Thank you.